Welcome to an introduction to structures and types of solids. So, we have two main types of solids. We have crystalline solids that look something like this, so something like sodium chloride, let's say, that forms a crystal. And then we have amorphous solids, something like glass, that we can shape into various shapes. We don't have a crystal that forms in this case, which means that with crystals, if we look at the local structure on a very small scale, it all looks the same. There's some sort of a grid pattern, a lattice structure that extends out in 3 dimensions. With an amorphous solid, it doesn't look that way. Now, there may be some order on a very, very small scale, but there isn't a long-range order. That scale doesn't repeat over a very long range as it does with these crystals. So within, say, this one large crystal up here, whatever the structure is up at the top, that structure repeats and repeats and repeats all the way down to the bottom. Now, once that crystal meets another crystal, say this one that's coming off next to it, at the join between those, there will be some difference between the structure, maybe. There may be some fault in between there. But within this one structure, within that one crystal, the structure is all basically the same. That's not the case with this class. So crystalline solids are solids with a highly regular arrangement of their components, and amorphous solids are solids with significant disorder in their structures. There may be some similarities with what's going on there, but there's still a significant amount of disorder within their structures. You don't have this nice crystalline arrangement of particles. So with crystalline solids, the positions of components within the crystalline solids are generally described using a lattice structure, looking something like this. So this is a three-dimensional system of points designating the positions of the components, so atoms, ions, molecules, whatever the solid is made up of. And we have something called a unit cell, which is the smallest repeating unit of the lattice. So we may have a unit cell that looks something like this. This is the cubic body-centered or body-centered cubic lattice. This is the face-centered cubic or cubic face-centered lattice. This is a hexagonal close-packed lattice. So we have different sorts of structures, and the properties of those structures will vary depending on what exactly is composing the structure and which structure it is. But they're all different lattice types, and there are many more lattice types as well. So crystalline solids can be classified into 3 different types. We have ionic solids, molecular solids, and atomic solids. So the ionic solids are solids composed of cations and anions, and each point in the lattice is occupied by a single ion. So this is something like sodium chloride. We have molecular solids, solids that are composed of molecules. So each point in the lattice is occupied by a single molecule. Not a single atom, but a single molecule. So this is something like sugar or ice. An ice crystal has, each point is composed of a single molecule. Now each molecule is composed of the various atoms. So in ice, the water molecules are each composed of hydrogen and oxygen and another hydrogen. Then atomic solids are solids composed of atoms. So here we basically have an elemental solid. So each point in the lattice is occupied by a single atom. So this is like iron or solid xenon, if you solidify it, carbon, like in graphite or diamond. So atomic solids can further be classified into metallic solids, network covalent solids, and noble gas solids. So the metallic solids are atomic solids of a metal or metals, maybe an alloy. Metal atoms are held together by metallic bonding, which is a type of delocalized, non-directional covalent bonding. Metals can also be described as positively charged nuclei in a sea of electrons. So each of the nuclei are close enough together, and the electron clouds of the atoms are close enough together that the outermost electrons, those valence electrons in the metals, are bound fairly weakly, and that means that an electron that's in between, say, 2 nuclei, it's not really bound to one nucleus as opposed to the other, and that means that the electrons can sort of flow around through this whole sea. So you end up getting this sort of sea of electrons where the electrons can move around, because the electrons just want to be near A positively charged. Well, as long as there's a nucleus around, the electrons will be around a positive charge. And so you have these positively charged nuclei, those islands in the sea of electrons, so the electrons can move, and this is what allows the metals to be, or what causes the metals to be electrically conductive. So they can conduct electricity, the electrons can flow from one side to the other relatively easily. So then we have network covalent solids. So these are atomic solids in which each atom is bound covalently, which is directionally, as opposed to the non-directional covalent bonding here. So they're bound directionally to its neighbor, and the entire solid forms one giant molecule. So this is something like diamond. In diamond, each carbon atom is bound to 4 other carbon atoms, but it's bound to those specific 4 carbon atoms because there are covalent bonds that are bound, that are binding those carbon atoms together, and each bond is, each carbon atom is bound. It has a tetrahedral geometry, which means that there's an angle of 109.5 degrees between one bond and the next. And that means that each carbon atom is in a very specific spot within the structure, and each of those carbon atoms is bound to 4 carbon atoms, and each of those is bound to 4, and so on. And so if you look at a diamond, it's essentially one giant molecule where all those carbon atoms are interlinked together. And that means that that whole thing is one molecule. It's a very, very strong sort of structure, and this is why diamond is the strongest substance that we know of, at least as of the recording of this video, and I don't expect it to change anytime soon. So these network covalent solids, diamond is the most common one. They're very, very strong bonds, very, very strong molecules, and it's essentially, one chunk of it is, that whole solid is essentially one giant molecule, which is why they're solids and not liquids or gases. Because in order for it to be a gas, then that whole molecule has to be moving around together. But of course, it's not going to do that. You'd have to basically atomize the whole thing, and that takes a lot of energy to break it apart. So then we have noble gas solids, which is when the dispersion forces are holding our noble gas atoms together. In order for the noble gas to become a solid, you have to cool it down fairly low. In fact, some of the noble gases like helium, you have to get really, really, really cold, and even then, it still won't solidify at 1 atmosphere. You have to get it to some pretty extreme conditions to get it to solidify. So that was an introduction to structures and types of solids.